Pronto? Pronto?
Hello, good afternoon all. The keynote address of the afternoon session is going to happen right now. So that I invite Dr. Marin Scaria to introduce the keynote speaker.
Thank you, sir. Good afternoon, everyone. Hari Om, and a warm welcome to the keynote session 2 of the International Conference on Recent Advances in Composite Materials 2024, ICRACM 24, organized by the Chinmaya Vishwavidyapeeth. We are delighted to have such an enthusiastic and diverse group of participants for this event. Before we begin, I would like to share a few pointers to ensure the smooth functioning of the session. Please keep your mic muted during the presentation to avoid any interruptions. We encourage you to actively listen and take notes of your questions during the session. Meantime, you can type your questions in the chat box for the speaker to address them later. Let us all maintain decorum by refraining from interrupting the speaker during their talk. Now, it's my privilege to welcome our esteemed keynote speaker, Professor Alessandro Pegoretti, a luminary in the field of material science and engineering. Professor Pegoretti earned his degree in material engineering from the University of Trento, Italy in 1988. He began his academic journey at the University of Trento in 1992 after gaining valuable experience in industry. Over the years, his career has marked by prestigious roles, including the visiting research scientist at the University of Connecticut, aggregate professor at the University of Modena, and eventually full professor of material science and technology at the University of Trento. He also served as the director of the doctoral school in material mechatronics and system engineering, and currently leads the Department of Industrial Engineering at the University of Trento. Professor Pegoretti's contributions to polymer and composite science are monumental, with over 330 referred publications, 2 books, 15 book chapters, and 3 patents to his name. His editorial expertise is equally commendable, serving as the editor-in-chief of Polymer Composites, the Engineering and Scientific Journal of the Society of Plastics Engineers. Today, Professor Pegoretti will share his insights on functional interfaces for structural composites, a topic that underscores his dedication to advancing materials for high-performance applications. Please join me in giving a warm welcome to Professor Alessandro Pegoretti. Over to you, sir.
Thank you. Thank you very much for the very kind introduction. It is really a pleasure for me to be able to deliver this talk. I wanted to be there with you, but unfortunately it was not possible. So please apologize myself for this. I will try to do my best to share with you some of the recent results we obtained in this area. First of all, let me just introduce briefly the University of Trento. It's located in the north part of Italy, in the border with Austria and Switzerland. It is a medium-sized university in the Italian panorama, so it has roughly 1650 16,500 students and roughly 1,600 professors and 11 departments. The departments of industrial engineering is one of them, and it is roughly composed by 100 people between academic staff and administrative staff, and 200 people between PhD and postdocs. And the area of research are ranging from materials, mechatronics, electronics, management, and biomedical. And these are also the area covered by master courses, which are all of them given in English. So it is also an opportunity for abroad students to attend. Today, I will focus my attention on functional interfaces for structural composites. So after a brief introduction, I will introduce the aim of the study, and then I will describe two areas in which we are currently working. One is the improvement of the fiber matrix interfacial adhesion, and I will show a couple of examples. And then I will move into another area, which is the self-healing of the fiber matrix interface. And also, I will try to provide two examples of the typical activities we are running here at the University of Trento. Just a brief introduction on composite material. I think it is not needed due to the type of conference, but we know that we are using composite material mostly because they are very light. It has a very low thermal expansion coefficient, and then at the same time, they are very stiff. They have a very high strength and a very good fatigue resistance. Applications are very wide, ranging from several applicative areas. The main one probably is transportation in terms of share. For us concerned the market, it is estimated that roughly 12.7 million tons are used worldwide in the recent survey by JAC Observer at the end of 2022, and this represents a market value of about $40 billion in terms of material and more than 100 in terms of components. Why it is interesting or necessary sometimes to focus on the interface? This was actually discovered years ago, when the first studies on interface and interfacial adhesion date back to 40 years ago, probably more than 40 years ago. And it is, of course, a region, the interface, in which a lot of properties are determined depending on the intensity of the adhesion, but also a region which offers opportunities to tune the properties properly of composite materials. In terms of interactions, we can range from intermolecular diffusion, chemical bonds, we can have electrostatic attraction, and also frictional roughening or thermal contraction or mechanical interlocking. These are the main type of actions which can try to tune in order to also adapt the mechanical properties of the composite material to the final application. In terms of experimental methods, it is quite interesting to observe that over the years, a number of different testing methods have been developed. The most rigorous are based on single fibers embedded in polymer matrices or in metallic or ceramic matrices, but mostly polymeric matrices. And some also tests regards the use of bundles of fibers, but the main one, if you browse the literature, are actually these two, the micro debond test, which is also widely used here in Trento. We have developed a facility to test our combination of fiber and matrices according to this technique, and the single fiber fragmentation test, which is also possible to be performed here in our laboratories. In the first case, the load necessary to debond a single fiber for a matrix, drop of matrix, is basically measured. In the second case, in the fragmentation test, we are measuring substantially the length of the fiber when the saturation of the fragmentation process is reached, which is proportional to the critical length, and therefore we can try to find a link between this critical length and the adhesion at the fiber matrix interface. In this area, how to improve or to modify the fiber matrix interfacial adhesion, there are two approaches. One is to modify the matrix, and the second one is to modify the fiber. In this talk, I will mostly focus on the second one, which implies some modification on the surface of the fibers in several ways. We can, for example, have a chemical modification by some chemicals that can be deposited on the surface of the fiber, typically silane or titanate are typically used. We can deposit or try to modify better the surface of the fiber by laser treatments. These are recently been introduced due to the rapidity of these treatments and the possibility to tune the effect, as I will show you later. Another possibility is to deposit either particles, for example, nanoparticles, on the surface of the fibers, and I will also provide some examples of the possibility in this field, or to deposit a continuous coating, for example, a polymeric coating on the surface of the fiber in order to tune some of the interfacial properties. And also in this case, we have some examples I can provide. It is why I call this talk multifunctional. I introduced also this adjective because really by tuning the fiber matrix interface, we have also the possibility to induce some functionality in the composite material which are not present in the uncoated or untreated fibers. For example, we can induce the capability in the composite material to sense some external stimuli, such as mechanical strain, for example. So we can monitor the strain by changes in the electrical resistance, and this imply the composite material should be conductive, which is not always the case. If you think, for example, at epoxy glass composite, these are typically non-conductive, but they can be rendered conductive by properly coating the fibers with in a proper way, or we can increase the damping properties of the material or reduce the damping depending on the need. Another very wide subject, which is quite intensively investigated today, is the capability to repair the composite material, the so-called healing or self-healing, depending on the external stimulus. And this regards also the possibility to repair the fiber matrix interface. So also this region can be repaired, as I will show you later in a couple of examples. So this brings me to the aim of this study, which is the interface tailoring. And in particular, we target two issues. One is to if it is possible, to improve the fiber matrix interfacial adhesion. And a couple of examples I would like to show you is to how we can improve this by depositing nanostructured materials such as graphene, for example, on the glass fibers, or how can we modify the chemistry and the porosity and the roughness of the fibers by laser treatments. And this technique was applied on basal fibers. And I will show you later the possibility, the results that we can reach in this area. Another area is, as I mentioned before, the possibility to repair somehow, to restore the initial mechanical properties after a debonding or a detachment of the fiber from the matrix due to a mechanical load. And in this area, we try to reach this in epoxy-based composite by depositing either thermoplastic nanoparticles on the fibers or a continuous film coating composed by a thermoplastic polymer on the surface of the fibers. And also in this case, these are very recent results that we published this year and also in 2024. And I will also show you and share with you some of these results. So let's start from the first topic, which is improvement of fiber matrix interfacial adhesion. And initially we started to work with this technique, which is a relatively simple one. So here in this slide, you can see the type of materials we use. So maybe an epoxy resin. We selected some e-glass fibers. And then also we produce some graphene oxide by using the standard Hammers method, starting from graphite. We disperse graphene oxide in water, basically, in a very mild solution. And at this point, we use electrophoretic deposition to force, basically, the coating of glass fibers of a layer of this graphene oxide. Here you can see the laboratory setup we use for this very simple experiment. The experiment is simple, but the effects are very interesting because you can see here how it is relatively simple to coat the glass fiber by a continuous coating composed by graphene oxide. And here you can see that changing the conditions, for example, the voltage using the electrophoretic deposition, it is possible to change the thickness of the layer deposited. It is also possible to reduce chemically the deposited graphene oxide to reduce graphene oxide, which at this point is a conductive layer, electrically conductive layer. How we did measure the effect on the adhesion? We used the single fiber fragmentation test. Here you can see the configuration. Basically, we embedded a single fiber in a coupon of matrix, and then we loaded this coupon, and with a microscope, we did observe the generation of fragments, which are quite evident in this picture. And at the end, when the saturation of the process is reached, you can reach a length, which is called saturation length, which is proportional to the critical length. This critical length allows us to determine the interfacial shear strength. This is the typical way these data are collected and analyzed in the literature. If you look at the effect, we can observe a clear increase of the interfacial shear strength when we increase the electric field using the electrophoretic deposition. Just let me point out that an increase in the electric field means an increase of the thickness of the coating, as is actually documented by this data, which reports the weight increase in the tissue, in the fabric that we use under different electric fields. For us concerned the improvement, we reach a very high improvement in the interfacial shear strength by more than 3 times by using graphene oxide, and a little bit less, around 8% by using reduced graphene oxide. And the situation is documented in this plot. A side effect, but this is a positive one, is for some application, is the fact that by using reduced graphene oxide, the resistivity of the composite is decreasing. In particular, if you look at this bar, we reach a conductivity in the composite material, or a resistivity actually, which is very low, which means a quite high electrical conductivity, especially in comparison to the uncoated materials. So we move substantially from an insulating to an electrical conductive material. And we test the material under tension, and simultaneously we measure the electrical resistance. And here the two quantities, the stress basically and the strain, and concurrently the change in electrical resistance are simultaneously plotted in this slide. And you can see that by monitoring the change in resistance, it is possible to have an estimation of the strain and therefore the stress applied in the composite material. So it's a possibility to monitor a structure, for example, by measuring the change in electrical resistivity. In order to scale up the process, because electrophoretic deposition, the equipment we used was a very small one, we use another technique, which is the tribo electrification. It is a very simple concept. So basically, when you are sliding two different material on the top of each other, you can generate the charging in one of the two, in both of them actually, and by selecting the proper triboelectric series, you can deposit or force to have positive charges on the surface of glass fibers. In this case, we use a Teflon rollers on which the glass fibers were rubbed. At the end, we basically, you get a positively charged fiber, and if you have a bath, like in this case, containing negatively charged graphene oxide, you can obtain a coating on the fibers by a very simple technique. Here you can see some pictures on the coating we reach. Basically, here you can see different percentages of graphene oxide in the solution, and also different intensity of the rubbing against the Teflon rollers. And in particular, we measured the debonding, the micro debonding, by using a very simple test that I already introduced before. And by measuring the maximum load, and the maximum load can be normalized to the contact area between the drop and the fiber, you can obtain, it is possible to obtain an interfacial shear strength. This interfacial shear strength, IFSS, in megapascal, is plotted here as a function of the intensity of the rubbing between the two materials, the glass and the Teflon, the glass fibers and the Teflon rollers, and also as a function of different concentrations of graphene oxide, reduced graphene oxide, sorry, basically on the surface of the fibers. With a proper, by optimizing the condition, it is possible to increase the addition of the initial one by a factor of 0.5 roughly, so roughly 50%. And this is basically how we can improve the addition in a relatively easy way. Another possibility is to use laser treatments. Here, basically, we use basal fibers. This was a collaboration, actually, with some colleagues in Finland and also in Spain. And here, basically, you can see the treatment of the basalt or fibers or glass fibers. And we use both of them, but the study mostly will focus on the basalt fibers. So the scanning can be performed in a relatively fast way, and the power of the laser can be changed. And this is, of course, leading to different effects on the fabric. In particular, by using both optical and scanning electron microscopy, you can observe the effect, which is changing with the power used during the treatments. And in particular, if you look at the picture, you can see that after a given power, the fabric is damaged, so it is not suggested to use a power which is too high. And on the other hand, if the power applied is too low, there are basically no effects on the fibers, and therefore we have to optimize these processing parameters. How we did measure the effect, here it is quite interesting, because we established a collaboration with some colleagues in Finland, in particular the University of Tampere, and also with a spin-off of the University of Tampere, which is Fibrobotics. This company is producing a tool which is very interesting because it allows to perform the micro debond test in a much automatized and faster ways. Here you can see basically a movie that we took during the test. It is actually the preparing stage, during which you can basically deposit a single drop of resin on fibers, both carbon and glass fibers. In this part of the movie, you can see the fiber we use. In that case, are glass fibers. the glass fibers are measured, the diameter, and basically, and next we have to deposit the resin. So we start from a liquid pot of resin, which is in this area of the device, and the fibers are pulled through the bath in order to generate these small droplets on the fiber surface. In basically this movie, you can see the formation of these droplets. Of course, depending on the viscosity of the resin and the velocity of the fibers, we can reach two conditions. Either we can deposit droplets, like in this case, or by reducing the speed, we can deposit a continuous coating on the fibers. Here is another movie in which you can see the test performed by the same machine. So after the droplets are deposited on the fibers, it is possible to test the fibers by performing the pull-out, the micro-debonding directly in the testing machine. Now the movie started, so you can see basically the fibers which are moving, and now we reach a contact between these grips, and the force starts to increase until we reach a break. So basically we separate the fiber from the matrix. Of course, the load does not drops to zero because we have some friction between the fiber and the matrix. So this plateau represents the frictional forces between the fiber and the matrix, which are also interesting to be measured. The maximum force is here, and from this maximum force, we can measure the interfacial shear strength according to a model. The advantage of this technique is that a lot of points can be collected, so we can change the droplet area because by using the microscope on the machine, we can measure the size of the droplet, and the size is changing droplet by droplet. So we have a plot of the maximum force, which is the force I showed you before during the test, as a function of the droplet area. The slope of these lines represent the interfacial shear strength. So it can be converted into an interfacial shear strength, IFSS. And for us concerned, the laser effect, the effect of the laser treatment, we can see that initially, when the power increases, we get a decrease of the interfacial shear strength. Probably here we are just removing the coating on the fiber, the sizing. And after we can have some positive effect, but with a limited extension. So at the most we reach 8%, but with a large standard deviation. So basically we are not very much satisfied until now with this technique, but we are still evaluating if some improvements can be reached. At this point, I would like to move to the second part, which is more on the self-healing and how we can repair a broken interface. Of course, this process cannot be performed in a standard composite material composed by carbon or glass fiber in an epoxy matrix, because epoxy is a thermostatic material that cannot be repaired easily. So in order to reach this, we have to use several techniques. The one we decided to use is to deposit a thermoplastic material in form either of nanoparticles or a continuous film coating on the surface of the fiber. At this point, if there is a layer of a thermoplastic material on the surface of the fiber, we can imagine to apply a temperature increase in order to melt the thermoplastic polymer and to somehow restore the initial adhesion. Of course, the thermoplastic polymer must be properly selected. One of the main thermoplastic polymers used in this field is polycaprolactone, PCl. It has been widely studied. For example, in Lausanne, EPFL, Professor Michaud it has also a spin-off company of which is producing prepreg containing polycaprolactone, which is very active and very can induce a repair of the polymer in the composite material. So we selected this polymer, which has a relatively low melting point, around 60 degree, and therefore it is suitable to be used also with standard epoxy matrix. We select a standard epoxy matrix and also glass and carbon fiber. So we use both type of fibers in these investigations. How we did coat the fiber with nanoparticles. Of course, we are first to generate a stable suspension of nanoparticles of polycaprolactone in water solution. And this took us some time because it is not easy to find the right ingredients of this in order to reach this condition to impede basically the coalescence of this very small particle. But at the end, we manage this. And then we use this solution containing negatively charged polycaprolactone nanoparticles by using electrophoretic deposition, which is a technique I already mentioned before. And with this technique, it is possible to force the charged particles to migrate, to move on the surface of the glass or carbon fibers. Here you can see some data about the size basically of the particles. They were under 100 nanometers, so relatively small, without distribution, of course. And here you can see a picture of how the glass and carbon fibers can be coated quite efficiently by using this technique by relatively small particles of polycaprolactone. At the end, we did measure the initial adhesion, and then after the fiber matrix interface was damaged and broken, we healed basically the material at 80 degrees C for half an hour, and then we tested the adhesion again by using the device I showed you before, which again was used in a collaboration with the University of Tampere in Finland. So in this way, we can measure healing efficiency, which is basically the ratio between the interfacial shear strength in the healed system over the interfacial shear strength in the unbroken system, which is the initial one. Which values we were able to obtain. Here you can see a summary of the result on glass fiber coated with nanoparticles of polycaprolactone. Positively, we observe an increase of the adhesion by the deposition of nanoparticles. And after basically the fibers matrix interface is damaged, we were able to reach a healing efficiency, which means how much of the initial adhesion we can restore, of about 50%. Okay, so basically half of the initial adhesion can be recovered by using these conditions. If we move to carbon fiber, we basically observe a different situation. We reduce the initial adhesion by about 63% in comparison to the untreated fibers, but the healing efficiency was 100%, which means that basically we're able to restore completely the initial adhesion after the damage introduced in the fiber matrix interface. Now, we actually decided to investigate by using exactly the same materials, so epoxy, glass fibers, and polycaprolactone, the possibility to reach a continuous coating on the glass fiber by using the same machine I showed you before, of course, by changing the velocity of the fiber to move into the liquid resin. It is possible to deposit a continuous coating of polycaprolactone on the surface of the fibers. According to our determination, the initial diameter of the fibers were 18 microns, And we were able to reach a final diameter of about 22, which was the highest diameter. And therefore, you can evaluate a thickness of the layer of the deposit PCL coating of about 2 microns. Here you can see the initial fibers uncoated. The diameter is roughly 18 micron. And then different velocities of extraction. By changing the velocity, the diameter increases until about 22 microns, which is basically indicating a coating which is quite homogeneous on the surface of the fibers, and it is composed by polycaprolactone. At this point, by using the machine I already introduced before, in collaboration with Fiber Robotics, we basically measure the adhesion with a large number of experiments. If you do these experiments manually, it takes too much time. It is not possible. So you really need an automatic machine to do this type of test, in which you can change we can deposit several droplets, more than 30, 40 on the same fibers, and then to test them in a quite automatic and continuous way. Again, by the slope of this of the regression line used to fit this data, you can get the interfacial shear strength. Here you can see the values. The initial adhesion was actually improved by about 23% by using this condition, a speed of 2.5 millimeter per second in the extraction. And basically, this was a positive thing. So we decided to focus our attention mostly on this condition. And we evaluate the healing efficiency more or less in the same way. So basically, we tested the fibers before and after healing, and we compare the results in a ratio which is called healing efficiency. At this point, we can go into the results. Here you can see for basically the conditions that we at the end selected, you can reach an increase. Basically, sorry, this is already the healing efficiency reported. So you can see that the healing efficiency is quite high. And here you can see 3 bars because we healed the interface 3 times consecutively. So we broke the interface once, then the second time, and a third time. So you can see 3 different values. The first value is the highest in general, so we can reach also values which are around 100%, so we can fully restore the initial adhesion. But after the first test, we observe a decrease in the healing efficiency. That was quite a surprise. I mean, at the end, we were hoping to be able to restore these mechanical properties more than 1 time consecutively, several times actually. And so we decided to try to investigate a little bit more what was occurring in this case. And in order to get some insight into the process, we did some modeling by using finite element method. And here you can see how we did model the situation. So here you can see the glass fiber, the PCL coating, the epoxy droplets, and the blade, which are the main actor. And then we analyze basically the process. What we did observe is that after the first healing, the droplet actually changes the geometry, of course, because it is in contact with the blade, so the geometry changes. And this change in the geometry, it is not taken into account in our calculation. So if I go back just a minute, in this calculation of the healing efficiency, we assume the same shape of the droplet. So we did not take into account the fact that each time we are repairing the interface, we have to test it, and therefore we are deforming the droplet. These are basically 3D images taken by the optical microscope, which is on the equipment. And by this, we were able to reconstruct exactly the geometry and to model the geometry by using finite element method. The results are reported summarized here. It is quite interesting to see that it is very, first of all, the predictions, which are the continuous curve, are following the experimental data very nicely. So we can reproduce the experimental data. And at the same time, we can observe that after the first healing, a drop in the force is observed due to the change in the geometry. So this drop in the force is not necessarily associated to a drop in the adhesion. So we have to take into consideration actually this effect in order to correct somehow the model and the prevision of the model on the interfacial adhesion. Okay, this brings me to more or less the conclusion of this talk. So I would like to summarize a little bit what I did show you. So basically, we are focusing recently our attention on the so-called tailoring of the interface region with two main aims. One is to improve the interfacial adhesion, and the second one is to possibly induce a healing or to generate a repairable interface. For the two areas, we explore several possibilities. One was to deposit by electrophoretic deposition or tribal electrification a layer of graphene, and then basically we use graphene oxide and reduce graphene oxide for this by reaching very important, very interesting results in terms of improvement in the adhesion. In the second case, we use a laser treatment. The results were less intense in terms of interfacial shear strength improvement, but the technique is very fast, very quick. It does not require any chemical. So maybe we will continue in this analysis in order to see if some better result can be used also by using this laser treatment. In the second part, we use a thermoplastic material deposit on the fibers, both glass and carbon fibers, in form of either thermoplastic nanoparticles or a continuous film of thermoplastic material. The material we select was polycaprolactam, and we did observe that it is possible to heal the interface, to repair the interface up to 100% in case of carbon fiber. And basically, we also reach 100% with glass fiber by using, in this case, a film rather than nanoparticles on the surface. I want just to thank some colleagues in the group, in particular Harun Mahmoud. He is now a postdoc here in Trento, and because he did part of his PhD project on this, and also Laura Simonini, who also is a postdoc now in my group, and he is also one of the main actors in this activity. I have also to thank the sponsor of this project, which is the US Air Force. I did most of this activity within this grant, and I would like also to thank you very much for the kind attention. And of course, I'm available for questions if any.
Thank you so much, Professor Pegoretti, for such an insightful and thought-provoking keynote on functional interfaces for structural composites. Your expertise and innovative perspectives have truly enriched our understanding on this critical area in material science. Now, we would like to open the floor for questions. In case you have any questions, you may now type in the chat box so that we can address them one by one. If there are any questions. Okay, Professor, we have one question. This one by Ms. Nivedita. How might emerging technologies such as artificial intelligence or nanotechnology play a role in advancing the study and applications of SRCs?
This is a very good question. We are now trying to understand how especially artificial intelligence can help us in making the test we are performing even more faster and to reduce basically the number of data points we are collecting. But really, we are really at the beginning of this, so I don't have a clear already information that I can bring at this level. Nanotechnology is another subject. We already, as you can have noticed, already use nanoparticles in this area in several cases, both graphene or also the polycaprolactone nanoparticles we use can be considered actually at this level of size.
All right. Okay. Thank you, sir.
Yeah.
Do we have more questions?
I see there is a Joseph asking.
Yes. I want to refer to your grant. What is the application of such composites for energy storage?
Yeah. Basically, we are now using phase change materials and to accumulate thermal energy. And therefore, we are also using the same techniques, the coating of polymer thermoplastic particles on the fiber surface. And this is the reason why basically we are interested also on how this can affect the adhesion. Yeah, this is the main reason why we are basically working in this area in collaboration with US Air Force. Yeah.
Thank you.
You're welcome.
Okay. We have one more question by Ms. Kopika. What challenges are encountered in ensuring uniform graphene coating on fibers, especially for large-scale applications?
Yeah, this is another interesting question. In fact, if you notice, we move from electrophoretic deposition to the tribo electrification exactly to scale up the process because it was quite difficult to enlarge the electrophoretic deposition to very large surface area like fabrics. But it can be done. So it basically, of course, our study limited the size to the coupon level, but it is possible to deposit very large, even very large surfaces by using different techniques.
Thank you, sir. One more question by Rosemary Tommy. What specific techniques are used to fabricate microcomposites for studying interfacial properties, and what challenges are encountered in these processes?
Well, there are several techniques. One the more promising is the one I show you regarding the micro debonding, because it can be automatized. So the machine I show you, it can be it is accessible commercially. So they are selling this machine mostly to companies which are working in the research field. Which are producing fibers, so they are very interested in optimizing the sizing and the coating of the fibers. But in principle, even research centers can buy this type of machines in order to automatize and to make the single fiber pull-out test or micro debonding test to be faster. For us concerned, the fragmentation test, I'm not aware of automatic machines. We have to do it manually. And it takes more time. So in general, I would say these tests are quite time consuming if you don't have an automatic machine. It takes quite a lot of time. Yeah.
Thank you, Professor.
You're welcome.
I think we can now conclude the QA session. Once again, thank you so much, Professor Pegoretti, for being with us here today. And thank you for everyone who joined us to make this an engaging and interactive session. Have a good day, everyone.
Yeah,
Thank
let
you.
me just only thank Professor Srivastava, Vijay, because it was due to him that I'm in this session, and I would like to say hello to him and thank you again for inviting me.
Now, Professor Srivastava, your mic is muted now. You can unmute and
Thank you very much, Professor Alessandro.
Thank you. Thank you, Vijay. See you. I hope to see you soon. To meet you
Okay,
soon.
thank you.
Yeah. Bye-bye. Thank you
Bye.
again.
Thank you all. We will soon have our next keynote session by Dr. Maya Jacob John on bio-based solutions to implement circular economy for the biomedical sector. We will begin the session at 3 p.m. Thank you.